So, um, we're going to talk about oxymercuration here in this video, and we're going to get to another addition reaction, another acid-based addition reaction that goes through um, carbocations, and talk about how rearrangements have an effect on this. So, all right, next up, on the wrong slide, oxymercuration. Okay, so in oxymercuration, what oxymercuration looks like is you've got an alkene again. I'm going to use one of the alkenes that we recognize from our rearrangement video. And then an oxymercuration is a two-step process. And these two steps are always carried out in sequence. So we just put them both over the same arrow. So we have a mercury compound called mercuric acetate. We'll talk about that here in a second, plus water. And then our second step is sodium borohydride. So first of all, let's talk about what the product of this is. So the product that we get out of this reaction is going to be an alcohol where the water ends up adding to the more substitutive position of the alkene, right? So we end up with an OH over here. But of course, and then we get a hydrogen at this position. And what you'll notice is that there is no rearrangement in this case. Right? So what we talked about in previous videos was that when we have a cation at a secondary position next to a tertiary position, that cation will rearrange to make a more stable cation. In oxymercuration, we don't have to worry about rearrangement. Right? This is the real advantage of oxymercuration. So when we do oxymercuration, we treat mercury is a big H+. Mercury is just a replacement for H+. And we have to use mercury in order to get this no rearrangement idea, but reaction-wise, it's pretty much the same thing. And so the first thing that's going to happen is our pi bond is going to come add to mercury. And so we're going to make a carbocation the same way that we have before. And of course, we're going to make the carbocation on the more substitutive position of the alkene. So we end up with mercury attached over here and a carbocation at the secondary position. Right? And so this is secondary cation next to a tertiary position. And so normally we would say, yes, this is going to rearrange because the tertiary cation is more stable than the secondary cation, except that in this case, because we have mercury next door, the mercury atom is so large and has such a large cloud of electrons, right? So if you look at the periodic table, mercury is down there, way down in the bottom row of your periodic table. It's an atomic number of 80, so it's got just this huge cloud of electrons. And so these electrons are very far away from the mercury nucleus. They're very diffuse. Mercury is a very fuzzy atom, for lack of a better term, right? And so and yes, I did use fuzzy because of the cat. Anyway, yeah, so Mercury is this large fuzzy atom that has a lot of electrons to share. And so instead of just sitting here like this is not the actual form of this cation. What we actually get is the mercury kind of shares its electrons with the carbocation. So the carbocation is here at the secondary position, but then we have kind of almost a half bond to mercury. We make this kind of weird three-membered ring. But what this does is this mercury, so the electrons on mercury stabilize the cation, and make this stabilized cation, make this more stable than the tertiary cation. Right? Because if we put the cation at this tertiary position over here, the mercury can no longer reach it. And so we lose the stabilization of the mercury. And so basically the carbocation is making a choice. It can stay at the secondary position and have the mercury electrons kind of stabilize it by sharing their electrons with this carbocation, or it can move over to the tertiary position and get a greater substitution and be more stable that way. The carbocation always chooses a secondary position with the mercury present. So now our water comes in, attacks that carbocation, and notice that our conjugate base, our water, is still adding to the carbocation position, much like all the other reactions that we've seen. And we still have mercury here. Right, so now this cation, we can once again lose H plus to make this into its neutral conjugate base. And we're going to get OH and mercury. And then we get to the second step where we add the sodium borohydride. NaBH4 comes in, and all the NaBH4 does is replaces the mercury with a hydrogen. Right, so the mercury is there to stabilize this cation. Once that's done and the cation doesn't rearrange and the cation is gone, we can replace the mercury with hydrogen by using sodium borohydride. We're not going to go into the mechanism of that second step because it's a mechanism that's very complicated and we don't need to know it. And so what I'm more interested in you being able to remember and know about this mechanism is the idea of creating the carbocation. So this is still Markovnikov's rule, right? We're adding our hydrogen. Eventually, we're adding our hydrogen to the less substituted position. So that means we're adding our mercury to the less substituted position. And we're creating the cation at the more substituted position so that our conjugate base, water, can attack there. Right, so this still follows Markovnikov's rule. Right, which is great, but we don't have to worry about rearrangement. So oxymercuration actually ends up being the simplest one to where we can predict the products because the oxygen will always go to the more substituted position of the double bond. The hydrogen will always go to the less substituted position of the double bond, and we never have to worry about rearrangement.